In Volume 1, we looked at the basic points about preventive maintenance for operators. In Volume 2, we examined the basic structure of two vital pieces of equipment, motors and pumps, and fundamental cleaning procedures. Now we're going to move on to look at troubleshooting and corrective maintenance. The technique of improving equipment so that breakdowns will not recur is known as corrective maintenance. We'll be looking at examples of common troubles that can occur with machines and other pieces of equipment, in particular motors and pumps, and discussing how to proceed with corrective maintenance.
So, corrective maintenance is what we have to consider next. In particular, we need to find improvements which will make for easier cleaning and checking and prevent things from going wrong. It may sound completely different from preventive maintenance, but it still begins with cleaning. Let's see an example.
This factory produces radiator heat diffusers. Although the operators here are still using old equipment, it is all exceptionally clean. Poor yield rate, and materials waste amounted to more than $100 every month. Corrective maintenance was introduced along with thorough cleaning. They realized that the main culprit in causing short stoppages was filings piling up around the cutting machines. They instigated cleaning for 5 minutes after each production run, using original cleaning tools created by the operators themselves. Here's another area of the same factory. The problems in this workplace were basically caused by the extensive use of hot water and chemicals. They had around 400 breakdowns a month. They also decided to create standard checklists and initiated a regular checking timetable for everyone at the workplace. 5 minutes every day, 15 minutes at the end of every week, and 30 minutes at the end of every month. Through this experience, the operators have now become so skilled they can in fact check just using their senses without referring to the checklists.
It might be useful at this point to have a look at a typical maintenance checklist. And while you're doing that, think about what kind of list you need for your own workplace.
The checklist includes boxes to be checked on the left and space for comments on the right, and information such as the workplace location, the operator responsible, and the date. Here are the items to be checked. Lubrication. The area around the lubrication point is clean. The label or nameplate is visible. The tanks have been cleaned. The oil feeder is clean. Oils can be distinguished at a glance. Oil pressure. The filters have been cleaned. There is no oil leakage around pipe joints. There is no oil leakage around the control valve. The label is visible. Air pressure. The air filters have been cleaned. There is no air leakage. The nuts and bolts are properly tightened. The exhaust port is free of blockage. Rotation and vibration. The beds are level. There are no scratches or rust on the surface of the tables. The bolts are properly tightened. The rotating area is not worn or moving eccentrically. There is no backlash on the gears. Control. The indicator lamp is clean. All the lamps are working. There is no damage around the insulated area. The switches all operate firmly. There are no disconnected wires.
What we have just looked at is, of course, just an example of the kind of items included on a checklist. Original sheets have to be tailor-made for each workplace and included in the whole comprehensive checking system. As we mentioned before, it's easy for operators to overlook such basic pieces of equipment as motors and pumps. Of course, the maintenance specialists will always regard them as the heart of production operations. But it's important that every operator knows the checking procedures as well. So let's look at those checking procedures. First, for motors.
There are 4 basic areas to be checked: the exterior, the bearing, the external wiring, and the control panel. You can use your senses to check for abnormal noise, unusual smell, or excessive vibration. Possible causes of abnormal noise include foreign matter trapped inside the motor, a bent bearing, or defective centering of the central shaft. The most likely cause of an unusual smell is that the winding has overheated. Excessive vibration suggests loose anchor bolts or defective centering. Visual checking of the bearing area will reveal oil leakages, dirt, damage, and so on.
Maintenance specialists will, of course, do more precise checking using various types of instruments and gauges. Here are some examples.
Heat-sensitive labels are very useful for providing easy visual control. When the temperature is within normal limits, the label is red. If the temperature rises beyond the limit, the label turns black. A sound detector is rather like a doctor's stethoscope. It's used to pick up abnormal noise on the bearing. The level of noise can be checked with a noise meter. And accurate measurement of vibration can be done with a vibrometer. Obviously, all measurements have to be checked against the operating standards of the machine at the time of installation. DC motors and wound motors are fitted with a brush. The size of the brush sparks and their sound should be carefully checked. If the sparks are bigger than usual, the cause may be dirt on the brush, too much pressure on the brush, or excessive flow of current. The external wires supplying electricity to the motor should be checked. Is there any visible damage? Are they all correctly fixed? Is there any change of color around the connections? Is there any indication of excessive current or short circuits? The earth should also be checked and all the connections made secure. The galvanometer on the control panel must be checked to ensure that the full load current is within normal working limits.
Now for some examples of corrective maintenance applied to motors.
This workplace centres around the drying furnace process. There were various problems to do with the V-belts connecting the motor and the fans circulating hot air. They easily developed cracks and sometimes snapped. At first, it was assumed that the V-belts simply weren't strong enough to take the load for a long period, and they were changed regularly every 3 months. However, thorough checking revealed that in fact there was a problem with the centering of the pulley. This was due to looseness in the pulley set screw. They locked the set screw in place, and as a result, the V-belts now don't have to be changed more than once a year. In this plant, there was a problem with the roller conveyor using a motor with reduction gear. The shaft generating the power was not rotating properly and would often freeze up. The drive parts were located right beneath the conveyor. When the play in the chain became too great, the shaft and the gear would run idle. To prevent this, they stretched the chain tight, but this put pressure on the bearing. The solution was to place pillow blocks at both sides of the shaft so that the shaft was firmly fixed in place and no longer received the load directly from the chain.
Now let's turn to checking procedures for pumps.
In the case of pumps, there is a difference between the checking done at startup and that done during operation. We'll look at the startup checking procedures first. Checking the levels of the cooling water and lubricating oil is simply done by looking at the gauges. Maximum and minimum levels should be clearly marked. Next, check whether the packing gland is properly installed. Over-tightening of nuts can lead to insufficient dripping of liquid and thus overheating. The shaft coupling should be checked for sufficient play by turning manually like this. With centrifugal pumps, the inlet valve should be totally open for checking and the discharge valve should be closed. With other pumps, both should be open. With pumps that require priming water, water should be added to the suction pipe to get rid of any air left inside. The direction of rotation should be checked by switching the motor on and off several times.
Those are 6 items for checking carried out at startup. Now how about checking points during operation? Well, here are 5 important ones.
First, checking whether the intake and discharge pressure, as well as the electric current, are within the standard limits. The gauge should clearly display any abnormal variation. The upper limit for the bearing temperature is the air temperature plus 40 degrees centigrade. Temperatures above that are regarded as abnormal. With a packing gland, continuous dripping suggests everything is fine. However, in the case of mechanical seals, dripping suggests some kind of malfunction, and the maintenance people should be called in immediately. The level of vibration must also be carefully checked. Possible causes of excess vibration are bad setting of the pump, rotator damage, wear, and defective centering of the shaft. It can also indicate cavitation, which creates a vacuum inside the water pipe and the pump. Or it might be due to a water hammer, which is a sudden stop in the flow. Obviously, a lot of experience is needed to be able to differentiate normal noise from abnormal. Abnormal noise can result from cavitation, contact sounds within the casing, bearing friction, and so on.
There are many gauges and instruments available, but in many cases, nothing can beat our own senses. So use your hands, eyes, ears, and nose, whenever it's safe to do so. Now, let's take a look at some examples of corrective maintenance for pumps.
This pump used to supply cooling water developed a bad vibration problem. At first, the pump made an abnormal noise, but nothing was done about it. Things got worse. Eventually, the shaft overheated, and the result was total breakdown. Thorough checking revealed that the iron base plates between the pump and the concrete foundation had rusted through. The pump had tilted as a result, and extra load had been exerted on the shaft. The idea for corrective maintenance was to substitute stainless steel plates for the iron plates used as support for the pump. This solved the problem perfectly. Now for a problem with a mechanical seal. This pump is generally operated using the highest possible pressure and temperature. Because of that, before improvement, it was common to get evaporation taking place inside the mechanical seal. This caused bubbles to penetrate inside the pump, which created noise and vibration. To overcome the problem, a heat exchanger was attached to cool the liquid flowing through the pump with cold water. This served to control the temperature within the mechanical seal and prevented evaporation. In this case, the temperature of the mechanical seal area became too high and caused an abnormal sound. Checking revealed that the strainer was clogged inside the pipe and was preventing the flow of cooling fluid inside the seal. Disassembly and cleaning was required. Since then, regular disassembly and cleaning of the strainer has been included on the standard checklist in order to maintain full working conditions.
As we've seen, operators can find all kinds of minor defects by practicing cleaning and preventive maintenance. And corrective maintenance is the way to avoid breakdowns in advance. The way to aim for 0 breakdowns, 0 defects, and 0 accidents is through skillful and effective production line maintenance. We hope these 3 videos have given you some real insights into how to improve your own maintenance